SwayamPrabha. Digital India. Educated India.
Hello, I welcome you all in the course on refrigeration and air conditioning. Today we will cover multi-evaporator and cascading system in vapor compression system. In a multi-pressure system, for last two lectures we are dealing with multi-pressure system. Multi-pressure system. And multi-pressure systems, we have already covered in the last two lectures multi-compression system. Now, in multi-compression system, the compression has taken place in more than one stages, right? And instead of having two pressure system, because two pressure system means simple vapor compression system. This is a two pressure system. So, on a pH diagram. So, this is a two pressure system, and we have already done this multi-compression system where more compression takes place in more than one stages, maybe two stages or three stages. Another multi-pressure system is multi-evaporator system. In multi-evaporator system, there may be one compressor, right? Compression. For compression, there may be one compressor, but there are number of evaporators. Instead of having one evaporator, there are number of evaporators evaporating at different temperatures. Now, the benefit of this system is, suppose I want to have a deep freezer for the preservation, let us say is minus 40 degrees centigrade. I want to have a freezer also at let us say 5 degrees centigrade to keep the things. So, at these two temperatures, if I have a simple system, it is difficult to operate. I will have to make arrangements. But here, if I have a multi-evaporator system, we can expand the compressed liquid, sorry, not compressed liquid, this is condensed refrigerant at high pressure at state 3 in two different evaporators. And these evaporators are operating at different temperatures or different pressures. This type of system is known as multi-evaporator system. The multi-evaporator system is further classified as individual expansion valve system and multiple expansion valve. Multiple expansion valve system. Individual expansion valve means every evaporator has its own expansion valve. So, the refrigerant at state 3 is expanding in evaporator 1 and evaporator 2, and both the evaporators are having their own expansion valve. In multi-expansion valve is the refrigerant which is entering any evaporator is, let us say, evaporator 1 or evaporator 2. It is expanded in two stages. That is why it is known as multi-expansion arrangement. And there is third type of system which has number of two compressors or more than two compressors and more than two evaporators also. And this type of system is known as cascade system, or the arrangement is known as cascading. Now, in the cascading, there are two simple vapor refrigeration or more than two simple vapor compression cycles, and different refrigerants are used in different cycles. We will discuss this cascading in details. First of all, we have already covered this, and now we will start with multi-evaporator system with individual expansion valve. Now, in this type of arrangement, there is one compressor. Earlier there used to be one evaporator. Now there is one compressor and one condenser. The vapor going from the compressor is getting condensed in the condenser. Now let us come to the evaporation side. The vapor is available here. Let us start from here 1. It goes to the evaporator 1, and before that it gets expanded. Then again vapor goes to evaporator 2, and then again it gets expanded in expansion valve 1 and expansion valve 2 respectively, and this is E2. Now vapor is emerging from E1 and E2 as well. So this is state 1, this is state 2, this is state 3, and this is state 4, let us say state 5. Now pressure at state 5, 4 and 5 are not same. Pressure are different because here expansion is taking place earlier at higher pressure. So pressure at state 5 is not same as the pressure at state 4. State 5 is not as the pressure at state 4, and we have only one compressor, and there is only one compressor is available for this purpose. In this case we have no other choice but to expand this vapor available at 4 to the pressure of 5, and here at pressure 5 it is sent to the compressor. Now if I want to depict this process on pressure enthalpy diagram, on a pressure enthalpy diagram, there is a saturation line, x is equal to 0, x is equal to 1. This is condenser, and at the exit of the condenser the state is 1. Expansion is taking place in one first expansion device, and we are getting state 2, and state 2 the vapor is entering the evaporator and coming out of at state 4. Now further in this down the line, this vapor continue to expand up to state 3. So 2 it is expanded up to state 3, and after attaining state 3 it goes to the evaporator 2. This is E2, this is E1, this is condenser, and after heat exchange in the second evaporator it emerges as state 5, and here we have state 4. What we should do? We should here reduce the pressure at the exit of the evaporator 1 through throttling. So in a throttling process enthalpy remains constant. So through a throttling process the pressure is reduced and mixing takes place. Here mixing takes place, and after mixing the mixture it goes to the compressor and compression takes place, and we attain state 6. So this is an arrangement of multi evaporator system. It is very useful, especially in the shopping area. It is very useful where some of the items for some of the food products we can preserve at a very low temperature, let us say minus 40 degrees centigrade or minus 30 degrees centigrade, and some of the items which are to be preserved on a higher temperature, maybe minus 10 or 0 degrees centigrade. So we can have this type of arrangement where we have two evaporators, and both the evaporators are operating at different temperatures. So this is the arrangement for multi-evaporator system with individual expansion valve. We can have another arrangement also where there are multiple expansion valves. In this type of arrangement, we will start with the compressor because we have only one compressor. So we will start with the compressor. So there is a compressor and there are two evaporators again. This is E2 and this is E1, and there is a condenser. And vapor is, after condensation, again the vapor is emerging from condenser. Vapor is emerging from, sorry, the liquid refrigerant is emerging from the condenser, state 1, and the entire liquid is expanded in one expansion valve, and we get the state 2. So state 1 to state 2, we get this expansion we get in one expansion valve. This is state 2. And after then attaining state 2, the vapor enters the evaporator 1, part of the vapor, and the process then it picks up heat in the evaporator and we get state 3 here. Now remaining part of the expanded vapor, which is available at this pressure is again expanded, and a flash gas type of removal arrangement is also provided here, so that only liquid enters here. Only liquid enters here and we get these processes. So liquid enters here means that is state 4. That is state 4. After expansion is state 5, and then we get state 6. Now after attaining state 6, again these two have to be mixed, and for mixing again there is same issue that this pressure has to be reduced to this one. Okay. So again throttling takes place here and mixing of both the refrigerants, and then compression in a compressor. So this is how the multi-expansion multi-evaporator system works. It is called multi-expansion because refrigerant is expanded in 2 stages for evaporator 2. And now these are connected, yes, these are connected, and it goes to state 7, and then it is compressed and get state 8. Now one arrangement we can make here. In this type of system, instead of having one compressor, if we provide 2 compressors, now we have variety of components with us. We have flash gas removal system, we have multi-compression system, we are versed with multiple evaporator system with individual expansion valve, evaporator system with multiple expansion valve. So we can have combination of all these arrangements to find to develop a system which can give the best performance. So instead of, it is also recommended that instead of expanding vapor from state 3 to this state and then again compressing it, instead of that, if we are able to make use of 2 compressors, instead of using one compressor, there are 2 compressors and one compressor for this, and both the compressors are compressing gas up to state 8. So this type of arrangement if I want to make here, then definitely in fact they are not parallel lines, they are diverging lines. So instead of drawing them like this, I will like to draw them like this. So we will get this type of pH diagram for multi-expansion arrangement. Now the problem with these type of multi-compression system, the pressure ratio is high. These systems are used where the pressure ratio is high. But the problem with the multi-expansion systems is that a refrigerant, suppose I'll give you some numerical values, then things will become clear to you, because sometimes it is not possible to use same refrigerant at a wide range. For example, in chemical applications, we require temperature of the order of, let us say, 100 degrees centigrade. Or in some of the applications, we require temperature as minus 80 degrees centigrade or minus 60 degrees centigrade. Condenser temperature is 50 degrees centigrade or 40 degrees centigrade. So this temperature difference, temperature variations is very high. This temperature variation is very high. Similarly, corresponding pressure ratio, Pk by Po or P2 by P1 or pH by PL. Pressure in condenser and pressure in evaporator. This ratio becomes very, very high. For a certain range, we can go for this multi-compression system, but for pressure ratio it is okay. Multi-compression system can be accepted, but for this wide variation in temperature, same refrigerant may not be recommended for the use. Let us look at the properties of some of the refrigerants. For example, R22. So R22 has normal boiling point minus 40.81 degrees centigrade, right? So if I am using this R22 at minus 20, the pressure is 2.45 bar, and if I am using R20 at minus 80, it is 0.1037 bar. Remember, the moment we reduce the pressure, specific volume increases. So the moment we reduce the pressure, the specific volume increases. The specific volume increases. Here also you can see for this R22, if the evaporator temperature is 80 degree, minus 80, the pressure is only 0.1 bar, and specific volume is also very high. It is 1.7782 meter cube per kg. And if you look at the refrigerant R23, it is normal boiling point is minus 82 degrees centigrade. So at 1 atmospheric pressure, it will boil at minus 82.2 degrees centigrade, and specific volume is only 0.1923. Specific volume is important because specific volume at the exit of the evaporator decides the size of the compressor. So specific volume of the vapor at the exit of the evaporator should be as low as possible. That is one thing. Second thing is, if you look at pressure at 40, suppose I choose 23, okay, for minus 80 it is okay, it is giving minus 82 degrees centigrade, at normal boiling point is minus 82 degrees centigrade. So it will boil, suppose I want temperature minus 80 degrees centigrade, R23 will boil below the atmospheric pressure, it is okay, I can use it for minus 100 also. But the problem is when it is taken at 40 degrees centigrade, it is critical temperature is 26.47. So I will be operating the system above the critical temperature, and the COP of the system will reduce. So I cannot use this refrigerant for this purpose. And similarly, if I use low pressure refrigerant, that is R123. R123 is okay when the pressure is 40 degrees centigrade, pressure is 1.5 bar, 1.5 times approximately atmospheric pressure, it is okay. But when I use R123 at minus 80, the pressure is 0.0013 bar, it's very, very low, right? And in that case, the specific volume is also very high, minus 80, the specific volume is 83.667. Huge amount of vapor has to be handled by the compressor. So now we have two options, we have to trade off. We have low pressure refrigerants is like R123, which are at higher temperature, at condenser temperature, their pressure is 1.5, it is okay. But on the evaporator side, they have very high specific volume. So if I use this refrigerant, the size of the compressor will be very large, that is not recommended. If I use high pressure refrigerant like R23, in that case, evaporator side is okay. The refrigerant will evaporate at minus 82 degrees centigrade, it is its normal boiling point. specific volume is also good, 0.1923, very small specific volume. But when it comes to the condenser, it becomes supercritical. Same is case with the ammonia. So you take any refrigerant. So we can see that any of the refrigerant which we have to deal in a very high range of evaporator and condenser, let us say -100 to 50 degrees centigrade, the difference is approximately 150 degrees centigrade. One refrigerant cannot work. And there are many other reasons for going for cascading system. I am just justifying why we should use a cascading system. The single refrigerant system is used in the system. The refrigerant should have high critical temperature and low freezing point. Farther we operate from critical temperature, more we are close to the COP of a Carnot cycle. So COP of the system, COP of the cycle increases when it operates far away from critical temperature. So that will not be possible when we use a single refrigerant for such a wide range. The operating pressure with the single refrigerants become too high or too low, that I have explained to you. Likelihood of migration of lubricant oil from one compressor to another leading to a compressor breakdown. Yes, this happens in multi-staging compressors when refrigerant from one compressor enters to the other compressor. In that case, the lubricating oil also shifts to the another compressor, and the lower pressure compressor becomes the short of lubricating oil. So that is another problem in multi-staging. And very low temperature in evaporator and large suction volume for high boiling refrigerant, that I have already explained you. If the high boiling refrigerant means normal boiling point is high, in that case if we take that refrigerant for the application of very low temperature, the specific volume will be high, and that is also not acceptable. The high pressure in condenser for low boiling refrigerant, high pressure ratio, low COP. So if we go for a single, if we take a single stage simple cycle for vapor compression cycle, so definitely the moment the pressure ratio increases, the COP of the cycle goes down. And operation of equipment on low temperature, I am talking about -100, -120 or -150 degrees centigrade, that also becomes difficult. So in order to avoid this, a cascading system is recommended. Now in cascading system is nothing but a combination of two simple vapor compression cycle or two or more vapor compression cycles. It means we have one vapor compression cycle which has a condenser, a simple vapor compression cycle, compressor, expansion device, evaporator. So this is TO1 and this is TK1. Temperature of condenser 1, temperature of evaporator 1. Now this is one simple cycle. A particular refrigerant for use this cycle may be here temperature -80 degrees centigrade, here temperature may be 0 degree or -40 degrees centigrade. Now this condenser is used to take away. Now how the condensation will take place here? Suppose the temperature here is -80 degrees centigrade and temperature here is -20 degrees centigrade. Now how the condensation will take place here? For the condensation of vapor at -20 degrees centigrade, we need to have fluid which has temperature lower than this, right? So we cannot use air, we cannot use tap water, water cooling is avoided, is not possible, air cooling is not possible. The possibility is that we have another vapor compression system, which has evaporator temperature less than this one. So there is another vapor compression system, this is TK2, and it has also its own expansion wall, and it has evaporator TO2, and then it has its own compressor. Both the systems are working with different working fluids. Now these systems are made as one heat exchanger, or this is known as cascading. So the heat of this condenser is taken away by this evaporator. So this evaporator may be at, let us say, -25 degrees centigrade, operating between -25 to 35 degrees centigrade. I am just taking some values so that you can have clear cut insight of the phenomena. So, I am repeating, in a cascading system, we can have 2 or more simple vapor compression refrigeration cycles. Each cycle has its own compressor, evaporator and condenser. Let us take one cycle, suppose we have to maintain minus 80 degrees centigrade, and one cycle will operate minus 80 to minus 20 degrees, for example. I am just giving an example, and here the condensation of vapor is taking place at minus 20 degrees centigrade. Now, in order to condense this vapor, we need a fluid which has temperature lower than the minus 20 degrees centigrade, right. So, the air cannot, normally the air cannot be used, water cannot be used, tap water cannot be used. So, what we have done, we have introduce another cycle which has evaporator temperature, let us say minus 25 or minus 30 degrees centigrade, and these two are clubbed, or a heat exchange is arranged between evaporator of higher pressure to evaporator at lower pressure or condenser at lower pressure, and in this case the condensation of vapor will take place in this condenser, and this heat will be taken away by this evaporator and it will go to this cycle. So, and we can have similar type of arrangement, 2 or 3 similar type of arrangement, and this is known as cascading of vapor compression system. We assume that the COP of this refrigeration cycle is equal to the COP of this refrigeration cycle. So, if the COP Carnot cycle, so Carnot cycle working between this temperature, between this temperature is equal to the COP of the Carnot cycle working between this temperature. So, TO1 divided by TK1 minus TO1 is equal to TO2 divided by TK2 minus TO2. Now, in ideal case, we assume that TO2 is equal to TK1. If we assume TO2 is equal to TK1, then TO1 divided by TO2, this TK1 is replaced by this temperature we assume is equal to this temperature. So, TK1 is equal to TO2 minus TO1 is equal to TO2 divided by TK2 minus TO2. Now, we cross multiply TO1 TK2 minus TO1 TO2 is equal to TO2 TO1 TO2 square minus TO1 TO2. We have just simply cross multiplied this, and you can see on the left hand side TO1 TO2, this will be cancelled out, and we will be getting TO2 is equal to under root TO1 TK2. It means approximately, this is not exact value, but approximate value at temperature. This is approximate absolute temperature TO2 is equal to under root of multiplication of maximum temperature and minimum temperature. So, in a cycle, if I want to develop a cascading system for a temperature range of T1 and T2, T max and T minimum. So, T max multiplied by T minimum of the cycle, if I take under row of this is going to be the temperature of evaporator or condenser of high pressure or low pressure cycle. For the sake of heat transfer, we can have some adjustment in the temperature values, so that we can attain a design of a realistic system. So, that is all for today's lecture. Now, in next lecture, we will solve a typical example on vapor compression system. Thank you.